G'day guys, welcome to Lecture 6, Newton's Laws of Motion. Just before we get started on this, I want to talk about the word laws for a second here. Now, a law in physics is when it's something we can observe happening. It is not an explanation for why it happens. Why is the word theory in science, theory of evolution, theory of relativity. These are things that explain why stuff happens. Laws, though, are just observations about what does happen. That's not to say that they're not useful, it's just that I want you to clarify the language. Alright, here's your learning intention and success criteria. Please complete your KS table down below here. Pause the video while you complete that. Alright, so having a look through here, we can see we're understanding Newton's 3 laws of motion. We want to be able to apply them to some basic scenarios. So the first cognitive verb there, we can see you need to describe these with some examples. And so we need to know, well, the first knowledge, what are Newton's laws? We need to be able to identify some basic examples of forces. So what are some examples? And finally, we need to construct a free body diagram. Now this puts up a couple of things. Firstly, what is a free body diagram, because you've probably never heard this term before, and secondly, can you actually do that? Now I've changed over here from the how I was using in previous videos to a can, just to help you with your reflection of going back to your learning to ask yourself, can I do this? Because that's what we really want you to do here. Okay, now we're going to be looking at Newton's 3 laws across chapters 11.2, 11.3 and 11.4 in this video. Now there are some extra content in these chapters about types of forces that I will go over in video 1.7. So read through it as you're going through your studies, but don't stress too much about getting your head fully wrapped around it. You won't really need it to answer the questions at the end. And you can consider doing parts of 1.7 as well as 1.6 at the same time. Okay, so I want you to think about a couple of things. One, roll a ball along the floor. What happens to the ball? Or what happens to the motion of the ball? What's easier for your body to do, walking or sitting on the couch? Now, 2,000 odd years ago, Aristotle proposed that everything prefers to be at rest, and will try to do that. Galileo came along in the late 1500s and developed another idea whereby he tested rolling a ball down a ramp and then up a ramp at different angles. And he observed that it pretty much always returned to the same height. Now he made sure that there's very minimal friction on this, and rolling has very minimal friction as well, so he made this as easy as possible. And so he went with the idea, well, no matter how shallow I make it, it always comes back to the same height, so what if I made it flat? Okay, where would it end up? And he wanted to show the idea that it would just keep going on forever. Right? Now, Galileo called this inertia, that things keep doing what they're already doing. And Newton read Galileo's work and developed his first law of motion. Now, Newton's law's got a few ways of writing definitions. The text has quite a good one. I recommend you do take a look at that one. Here's the one I was given in grade 10. An object at rest remains at rest, and an object in motion remains in motion unless an external force causes it to do otherwise. There might be a couple of extra words in there, but it's been a few years since grade 10. But it really comes down to one thing. Things are lazy. They want to keep doing what they're already doing. Now, there are a couple of things we need to really pay attention to this. One, the velocity is constant. Okay, velocity is always going to remain constant. So here I've written delta V, change in velocity, is equal to 0. Okay? Unless, if there's a force, then the velocity will change. So if the force on it is not equal to 0, then delta V will not equal 0. Okay? So, you right now, you are sitting there, you're listening, you're sitting very still. The forces on you are balanced, so your velocity doesn't change. You shift in the chair, the forces become unbalanced, so your velocity is no longer unchanging, it's no longer constant, you've had to change your velocity. Imagine you're riding a bike or a scooter at constant speed. The force of your legs are powering the wheels, the wind pushing against you, the friction of the tyres, these are in balance, so your velocity doesn't change. Note that I'm not saying your velocity isn't 0. That's a real big misconception students often have, that if something is moving, the forces must be unbalanced. No. if something is moving constantly without any change in its velocity, without any change of its magnitude, how big it is, without any change in its direction, then the force on it, or the total force on it, will be zero. Not that there are no forces, okay? The forces can be balanced, just that they are the total force, if we add it all up, would be equal to zero. Driving in a car at a constant speed is a really good example of this. There's wind resistance, there's drag, and so you push down the accelerometer a little bit just to apply a bit of force, and so then these two things cancel off. Okay. So Newton's first law, things about what causes a change in motion. Newton's second law describes the relationship between force, the mass of an object, and the acceleration that happens to that object. Now the long description is here. Okay. An acceleration of an object is directly proportional to the force applied and inversely proportional to the mass. We're going to look at those words in an experiment coming up. Directly proportional, what does that look like on a graph? And inversely proportional, what does that look like? All this means, though, is that if force gets bigger, acceleration gets bigger. That's what directly proportional means. As one goes up, the other goes up. And if mass gets bigger, acceleration gets smaller. Okay? And so if we make our mass bigger, then acceleration gets smaller. And this is commonly shown as this equation here. And you'll note this word net. Force net divided by mass is equal to acceleration net. It just means you have to sum up all the forces in order for you to figure it out. Okay? So if I have 5 newtons, so let's draw this for a second. Apologies. I need to make this editable. If I have an object that is of equal force, that's a terrible arrow. So this is 5 and this is 5. If we think about adding vectors, they're in different directions, so we'll say that this must be plus 5 and this would have to be negative 5. If we add these together, plus 5 plus negative 5 is going to cancel and become 0, so it's not going to move, or it's not going to change its motion. And that means that if it was still, it would stay still. If it was sliding along at 2 meters per second, it would stay moving at 2 meters per second. And so this is the net that we have to add these values up before we can do anything to work out the net acceleration at the end. Okay. Now there is a worked example on my next page. So here's a worked example from the textbook. An unbalanced force of 48 newtons west is applied to a 6 kilogram cart. Calculate the cart's acceleration. So again, we're going to do the same thing. What are our numbers? We've got a 48 newton here, and we've got a mass of 6 kilograms. So let's write that down. Force equals 68 newtons, and I'm going to put my direction to the west, and my mass is equal to 6 kilograms. We want to work out the acceleration. Now there's no other forces that's been mentioned here, so we don't have to add anything up. Acceleration equals force divided by mass. And I should be putting little vector hats on these. I told you in the first video I tend to forget that sometimes. So acceleration will equal 68 divided by 6. 68 divided by 6 is 11 and 2/6, which is equal to 11.3 recurring meters per second squared. Okay, so it's pretty straightforward. This formula is not particularly complicated. It's just that if you have acceleration and mass, you can work out a force. If you've got force and mass, you can work out acceleration. If you've got acceleration and force, you can work out a mass. And so it's just connecting 3 more ideas together. Okay. So let's have a look at Newton's third law. Newton's third law was written originally for every action there's an equal and opposite reaction, and the text talks about the problem with this word reaction. And I'd agree that there's an issue of implication of time. We're all very familiar with the idea of doing an action and getting a reaction from somewhere. And so the way the textbook presents it is the way I'm really going to emphasize it to you. Forces always occur in equal and opposite pairs. So these words equal and opposite still exist, but it's this word pairs here that's really important, because that's part of the secret of doing proper forced free body diagrams down the track. Equal in this case means that the size is always the same. If I push on you with 10 newtons, there is a push back to me with 10 newtons. The opposite is talking about direction. If I push forward, say I push against the wall pushes back towards me. Okay? So let's draw something out there. Let's say I've got two people, and this guy pushes on this person. There will be a pushback, same size, different direction, and that's what the opposite is talking about. Okay. So this is a picture from the text that I think is a really good one to look at for force pairs. This is a free body diagram. We have here a simple thing of a box sitting on a table, and the table is resting on the ground. And they've drawn 1, 2, 3, 4 pairs here. Underneath the text actually has a bit more description of this, and it's worthwhile reading that. So here we've got our first pair, and it's this terminology here, FBE, the force of the box on Earth. Let's write that out. FBE equals force of box on Earth. And so then the pair FEB equals force of Earth on box. So here we've got the force of gravity, that the Earth is exerting a gravitational pull on the box, but, and this is a bit weird sometimes to think about and might sort of throw you for a little bit, the box is also exerting a gravitational force on the Earth, and they are equal to each other. You are pulling the Earth up with the same force that it is pulling you down. The reason that we don't see the Earth moving all around the place because of all these people around it is because the Earth's mass is so big that the acceleration is not particularly large. Okay, and you can work that out for yourself. Here we've got another here we've got one called the normal force, and normal forces always happen when something pushes on something else. So when I write on here, there is a normal force, and that's what causes the text to start appearing. So the force of table on box, so the table is pushing against the box. Force of box on table, the box is pushing against the table. Okay? Gravity between the table on Earth and the Earth on the table. Here we've got the force of the ground on the table and against the normal force of the table on ground. And it looks like to me that they've mislabeled these. I would have put the force of ground on table here, saying that, actually I would have swapped these arrows around the other way. Same thing here. That the table on box should be pushing up that way, and the box on the table should be pushing down that way. Same thing here. The ground on the table should be pushing up, and the table on the ground should be pushing down. So I think they've got their arrow directions incorrect. I would have to chat with Walding about that. So this is a free body diagram, and we'll do a lot of examples on this in class, and we'll do some more demonstration of this when we talk about actual forces. So have a read through chapters 11.2 to 11.4 because it will talk about these forces in a little bit more detail, and I will go into them into more detail in another video as well. This video is just about Newton's laws of motion. So in this video we've covered three things. One, Newton's 3 laws of motion, so you should be able to describe those 3 laws. We've applied Newton's laws to a common situation, our acceleration object. We can see it's a very simple formula. And finally, we've represented some force pairs with correct notation, and that's appearing there on our free body diagram. Now, our entrance slip for this one is a little bit bigger. Okay, you've got 3 chapters here, 11.2, 11.3, and 11.4. In 11.2, I'd like you to do questions 3 and 4, and 1 to 4 in 11.3, and 1 to 5 in 11.4. Please submit all of these into the 1.6 space on eLearn. Okay, thank you very much, guys. Have a good night, and I will see you in the next video.